Hello, just in case you haven't watched previous video, I'm Ivan Fedyanin, software architect, and today we will continue our deep dive into consistency models achievable with leader-follower replication. So in previous video we have covered some introduction, problem statement, and some implementation specific of modern databases, which explain some nuances on why we could observe out-of-order writes or some replication lag even with synchronous followers. And today we will concentrate on eventual consistency in leader-follower systems, and we will review some examples and use cases when we could use it and when it's a very good fit for our purposes. We will start by recalling the definition of eventual consistency, and in simple words, it's such consistency model that guarantees that eventually all replicas will be in the same state and all of them will see the same writes if we assume that writes stopped on the leader and some time is passed, so the system achieved its stable, consistent state. Then whatever replica we choose, we will get the same values when reading from it. In the industry, there is some kind of uncertainty in a very strict definition of eventual consistency, and it relates to question of durability. For example, if we make some write and it's not durable, it will never achieve any replica and it will be lost. Can we call such system eventually consistent or not? And for our purposes, for this video and in general, we will consider that such system which does not provide durability will still be eventually consistent as long as all replicas will have the same state. Though there may be some lost writes, but they are lost on all replicas. And I want to show reasons for this. There are three fundamental articles which are done by masters of distributed systems. Let's see how they introduce eventual consistency. So theory says that all servers eventually receive all writes, and servers which receive the same set of writes will have same data contents. Werner Vogel, CTO of Amazon, who participated in the creation of famous DynamoDB, he says that all updates reach all replicas eventually. And Baylis points some problems in the definition. He notices that the definitions are not very strict. For example, database which always return number 42. When all replicas return 42, will it be eventually consistent, though these 42 were never written? And it's kind of not specified by the definition, because definition says that all replicas must see all writes and must return the same values when they read. From those definitions, it looks like authors agree that all replicas must receive all writes to call the system eventually consistent, but at the same time, Amazon DynamoDB, it allows to specify parameter w equals 1, which means that write can be accepted just by one server. And it's obvious that in that case, we can't really call that system durable, because if this one server dies, then we will lose the data. Actually, even if we have this parameter set to 5, if 5 servers have to accept the write and acknowledge it, they still can die. Basically, no matter how much servers will accept the write, if they die, then we will not get those writes back. It means that we can't really call any system durable, but nevertheless, we call DynamoDB, for example, eventually consistent. So no one doubts that it's eventually consistent. Okay, that was a bit long, but I just wanted to show you that definitions and articles, even by famous scientists, they are not always very formal and strict, and they leave us some rooms for different interpretations. But let's get back to our leader-follower system. Actually, it seems that in our case it's very easy, and in whatever mode we use our leader-follower system, it will be always eventually consistent. We can write to leader and read from follower. We could read from some specific follower, or we could read always from random followers. We don't need to specify any parameters about the visibility of writes, about lag of the replication process, about forbidding, for example, out of order writes. So basically, we can take any leader-follower system, we can use it in any mode, and we will get eventually consistent behavior. Let's consider an example of when we need to use eventual consistency, and in general, we use eventual consistency when performance is very, very important, and we want to optimize the system for maximum performance, and the temporal inconsistencies are not important for us, or they can just be easily handled by clients. In our specific example, we will look at enterprise configuration management system. In a nutshell, it's a database which stores configuration of feature flags, whether some feature is switched on or off. So basically, it's just one table, it has the name of the feature and its state. This system has one administrator who can make configuration changes, and it has a lot of services which constantly read configuration. And it's important that for now we consider a system with fully independent feature flags. It means that services will never rely on some mutual state of those flags. For example, that feature B is on and feature C is off. So they are fully independent. Now let's make several statements and requirements about this example. I'll go through them and I'll comment why exactly we made those requirements and statements. So there are quite a few of them. First is that write rate is relatively low, and feature flags are not updated often, maybe just several times a day. Why we made these requirements? Because we know that with leader-follower system we can't really scale writes very well, because of all writes they should go through a single leader, and because of this we just say that we will use that model in the system which has a low rate of writes. Next statement about this system is that there is very high rate of reads of feature flags, because we have multiple services, maybe thousands of them, maybe more, and they constantly read feature flags. And we made this requirement because we know that in leader-follower system we can easily scale reads, because we can have multiple followers. Next, let's say that it doesn't matter for us if feature flag will be updated in each service with delay after it's changed by admin on the leader. And the second requirement, it doesn't matter for us if feature flags are flapping. For example, a client can see feature A is on, then it can see it off, then on again, and in that case it will not cause any problems for our system. Let's see why those two requirements can be reasonable for such system. Usually feature flags are used when we want to switch on some functionality for some portion of users, and in that sense it's reasonable to assume that it does not really matter if there is some small delay in propagation of those feature flags. Also, it might not be very important if feature is off or on. Well, in some systems it might be important, but for our example we consider a system when it's not important. And especially we made those two requirements because we know that in eventually consistent systems both of those anomalies are possible: replication lag and the flapping. Next requirement is that feature flags are strictly independent from each other. So basically, we will never rely on the fact that service will want to see some specific combination of beta flags. And also that each feature flag can be written, read, or propagated independently from each other. And it does not matter for us if updates are propagated in the same order or not. So, for example, if admin switches feature A and then feature B, it does not really important for us if client will first see feature A or feature B on. Those three requirements are important if we want to use eventually consistent system, because in eventually consistent system, all of them kind of how the system behaves. Also, it matters for us that writes which admin makes, they are made in some specific order determined on the moment of write. And this requirement we made because we want it to be matched with properties of system with single leader. Basically here we want to kind of artificially create requirements which would be very well covered by eventually consistent system with single leader and multiple followers. And those requirements, they make very good sense for specifically this enterprise configuration management system, as you can see. And having seen all of those requirements, we see that leader-follower system with eventual consistency is a very good match. So single leader is needed to order all writes which admin makes. Also, having the single leader is not a problem from scaling perspective, because by definition, write rate is relatively low. High read rate is addressed by having multiple followers, and making these requirements about independency of feature flags, it allows us to use eventual consistency and configure the system for maximum performance, because we don't really care about strict consistency. Now let's see an example how it would work together and why eventual consistency is fine here for us. Let's look at this feature flag storage system and look how it could be implemented internally. It could have leader, multiple followers, some balancer, and multiple services. And initially, feature A is switched off. Then admin make write on the leader and switches the feature A on. And the services, when they read, they just go to balancer and they are randomly distributed to random follower. So initially, for example, when service A makes the read, it could be just balanced either to follower 2 or follower 4, and it will see feature A is off and will behave correspondingly. Next, it's possible that during next read it goes to the balancer, and now it ends up on follower 1 or follower 3, and the service will see this feature on. And on the next read, it can get back to follower 2, for example, which has not yet received this feature A on state, and again we'll see it off. And we assume that our services is okay with this flapping due to eventual consistency, and they work fine with it, and eventually when all followers will receive the updates, it does not matter to where exactly they will be routed, all services will receive that feature A is on, and that's what important in our example. In this example, we are satisfied with eventual consistency, and because of this, we don't have any performance overhead related to some stricter consistency models. But in order for the system to accept eventual consistency, we made one quite important requirement that all feature flags are independent from each other. More or less complex transition scenarios assume that feature flags can be dependent from each other. Assume that we have, for example, a website which has some pages, and it has a main page with just links or references to the individual pages. And initially it has only two references to only two pages, and we want to add another reference to page 3 and want to generate this page 3. And assume that this page 3 is something we are not sure 100% that it will work in production. For example, it might use some backend APIs which could cause some performance problem on backend, or just something like that. And we don't want to immediately switch this on for all users of our system and risk that our backend will be broken. Or for example, we are not sure if this page is good enough or not, that it will work. And for some reason, we want to test it in production. So what we would do in that case, we could have two separate feature flags. One flag will be responsible for generation of this page and publishing it and making it available. And the second beta flag, it will be responsible just for adding the reference to the main page. And basically, when both flags are on, it's our target state when this page is available and the link to the page is visible as well. As an initial step, we could have this situation when we switched on one feature flag which generates the page, but we have not switched another beta flag which shows this reference on the main page. In this scenario, we could, for example, make some internal tests on production of this page, or we could share the link with some beta testers and they could check that it works before we switch this flag and we'll show it for everyone. However, there can be another situation which we want to avoid. This combination of feature flags when flag for page generation is off and the flag for displaying page reference is on. And in that case, users will see the reference link, they will click it, and they'll get broken link, and it will be bad user experience and a production issue. At first glance, eventual consistency will not work for us under such more complex scenarios when we have mutually dependent beta flags. Let's look deeper how it could be. So assume that admin changed the values of those beta flags in the correct order. So first it's switched on generation of the page 3 and then it switched showing the reference of this page on main page. And on the leader they will be in the correct state, but on the followers they could become visible in different order because of eventual consistency. As we have seen in previous video, it's possible in leader-follower replication systems. So follower 2 has the correct state, which is acceptable for us, and it corresponds with the order in which admin made the changes, but follower 1, it has incorrect or broken state, when the reference is showing, but the actual page is not generated. And if service reads from this follower, it will get broken link. And it's not acceptable. Let's see what transition between states eventual consistency allows us. Remember that we are considering those possibilities from point of view of client. In our case, the client is service A. And some followers can have those beta flags as off because the changes are not yet replicated. Some followers can have both beta flags on, some followers can have one beta flag on and other is off, and other followers can have opposite situation. So we can have any kind of follower in our system. And because we always read from random follower, our service will be able to see one of those 4 possibilities. All kind of those transitions are possible. Because when service makes the read, every time it's just balanced to a random follower. and one of the possibility is forbidden. So we see that under this requirement of mutually dependent beta flags and our data model, eventual consistency will not work for us. It means that in order for our system to work, we need to consider other consistency models, and let's see other a bit stricter consistency models which could help. First obvious solution is to use consistent prefix read. Consistent prefix basically says that clients are allowed to view the prefix of all writes. And it means that clients might see the data with some lag, but it's guaranteed that they will see the state which existed on the leader at some point in time. And we know that because on the leader admin has switched on those flags in the correct order, then it's guaranteed that we will see state which existed on the leader. So it will be either when all beta flags are off, when all of them are on, or when the first one is off and second one is on. And all of these possibilities, they are fine for us, because in this case there will be no link and no page, here there will be link and a page, and here there will be page but will not be the link. So all the possibilities are good for us, but in that case we still can have some flapping, because the only guarantee consistent prefix read gives us that each follower will have a state which was on the leader at some point in time. But still, if we are connecting to random followers, we could see first, for example, this state, then we could get back in time and see this state, and we can get this state. And we can just, connecting every time to each follower, we can get a random view on those flags, but every view will be acceptable for us. And another option is to use session guarantee monotonic reads. Monotonic reads basically says us that if client has seen some state of the system, has seen some writes, it's guaranteed to see them on the next read. And in that case, visibility will be changed only in that way. So first, if client read two states when it's off, during the next read it could see this possibility too, or actually it could go straight to this one. On second read, client will see a new beta flag, and on the last read it will see all beta flags. So you see that there is no this arrow backward. If we already have seen some state, we can't go into the past like in previous situation, or like in situation with eventual consistency. So the stricter consistency model, the less transitions are possible. In this case, strictly speaking, client could go straight from possibility 1 to possibility 3. But in that case, it will never be able to get back to possibility 2. So we have seen that using monotonic reads or consistent prefix reads solves problems for us and allows us to use our system with mutually dependent feature flags without any changes to our data model. So we just changed consistency guarantees of the storage. Now let's see if we can still keep eventual consistency, for example, not to increase performance overheads, but still satisfy our requirements to see beta flags in the specific order. And for this, we might just slightly change our data model. Initially, in previous scenario, let's see which data model we had. So we were storing all feature flags independently in separate rows, for example, of some table or in separate documents. And if we just will make a slight change and we will place all our feature flags in one single document and make assumptions that each single document can be written atomically to the database, then even with eventually consistent system, If admin changes this document, it can change it to any state. For example, it could change both features at the same time, or it can leave show page 3 feature off, but switch generate page 3 feature on, and it will write it, and then all followers will see those beta flags changed at the same time. So it would be impossible for the clients to see the incorrect state. We don't have to place all our feature flags in the same document. But we could place, for example, all dependent feature flags in the same document, and in that case, just with slight modification of our data model, how we store the data, we could choose the system still with eventual consistency, keeping our performance benefits of eventually consistent system. This example illustrates that which consistency models we need to use significantly depends on the application. And sometimes it's possible to modify our application slightly and use a consistency model with lower guarantees. And we kind of for free could improve our performance just using a weaker consistency model. And in our example, placing related features in one document, it does not really worsen our system significantly. To conclude this video, I just want to remind that in Leader-Follower Replication, eventual consistency achievable is very easily. So basically, in any mode, any leader-follower system will be eventually consistent. Just remember about durability and that under some configurations, writes will not be durable, and if durability is required, ensure that you configure the system properly. With this, we have finished our eventual consistency talk, and next time we will proceed with other consistency models in leader-follower replication. Bye.